Right, thanks. Yeah, so suppose my title is a little bit ambitious, and we're really not very far in this. And I'm also not claiming to be the unique approach doing this. I mean, I'm sure you can use some function analysis like representation theorems to kind of avoid, to talk about measures while avoiding to do actual measure theory. But so, given that this is the sort of applied category theory seminar, our approach involves categories. So category theory, and roughly how far you've gotten so far is that we have a reconstruction of spaces of probability measures, and ultimately, or sort of as the next step, we'd like to get to the actual theorems, the most basic theorems of probability theory, so things like the law of large numbers. That turns out to be not so straightforward. Surprisingly, we have other results though that seem, from a conventional perspective, much more sophisticated, like results from conversions of martingales, stuff like that. But today I just want to talk about the basic setup, and how our construction, our definition of spaces of probability measures, and give some indication of why this recovers the usual definition in terms of Borel-Radon measures on metric spaces. Okay, so what actually is a probability measure? And from the perspective of the applications, what we deal with in statistics are not really the measures themselves, right? But they're just finite samples. If you do an experiment and you just get a finite sample, and a probability measure is a sort of idealized version of a finite sample that is useful to work with in order to derive mathematical theorems. It's a kind of convenient idealization, but roughly speaking, it's an idealization. Of a finite sample. And these are the things that we work with in practice. And it's a very convenient idealization because in these terms we can construct things like normal distribution, stochastic processes, all the famous ones. And yeah, so how do we make this precise? This sort of kind of philosophical idea that probability measures are such idealizations. So I want to give one possible answer to this question now. So state our main theorem, and then I will explain in the rest of the talk what a theorem actually means, so what the individual parts and notions that I will use in the theorem, what those are, and give some idea of the proof. Okay, so to have a convenient point of be able to refer back to it, I think I'll state the theorem on this board. If everybody can see this well. Yeah. Okay, so this takes place in the category of complete metric spaces. So we call this C-met, note the C-met. So the reason to work with this category is because in probability theory, all the theorems involve some kind of approximation, like the central limit theorem, law of large numbers are all kind of quantitative, or at least topological when they talk about conversions. Yeah.
What are the morphisms? Are they like
right. Yeah. I was going to get to that. So yeah. So with the morphisms are the short maps or von Lipschitz maps. Which means that we're short means distance non-increasing, so the distance in y between any two points, between any two values of f is less than or equal to the original distance in the domain space. And now the statement is that what we construct is a graded monad P lower star. So the star stands for the grading, like maybe you see in algebra, graded algebras or chain complexes, this kind of stuff, one uses something like a star or a bullet to indicate a grading. On CMET, graded by another category that we call fin unit. I'll explain what that category is later and why it has that name. And I'll also explain what a graded monad is. And a monoidal Kahn extension. So this is the category of endofunctors of CMET, and a graded monad is going to be a lax monoidal functor from this monoidal category into a category of endofunctors. And through the Kahn extension, we can sort of squash that down, or merge that into a single, into a lax monoidal functor from the terminal category, and then this is just an ordinary monad. And so this is going to be P, and so we have Kahn extension. So a two-cell, universal two-cell, like this, universal natural transformation, and such that the following things hold. So P star is constructed purely combinatorially. So P star is about this is about the finite samples. And the combinatorics of finite samples. And through the Kahn extension, we get a monad P of probability measures on complete metric spaces. So P is a probability measure monad. And so as the functor, the underlying functor of the monad, what I mean by a probability measure monad more precisely is that the object that assigns to any object P, so this is going to be another complete metric space, and it's going to be the space of, so the underlying set of the space is going to be the set of random probability measures on X. With a finite first moment. I'll explain all of this stuff. So this is the underlying set, and the metric is going to be the what's called a Wasserstein distance on the space of L1 Wasserstein distance on the space of these distributions. And furthermore, such that there is an equivalence of categories between P algebras. So when you have a monad of probability measures, a P algebra is your space where you can form expectation values. It's a domain for random variables, so that you can integrate. So it's sort of a space where you can integrate. And so we've also shown that the algebras of P are, the category is equivalent to the category of these P star algebras. So we can interpret this as saying that we also have a combinatorial construction of integration, because this is again purely combinatorial, and it's again equivalent to the category of closed convex subsets of Banach spaces. So those spaces in which integration makes sense from this perspective are the closed, so integration in the sense of forming expectation values, or forming barycenters of probability measures. Those are exactly the closed convex subsets of Banach spaces. And while there's a number of limitations to this, maybe most strikingly that using short maps only does not really seem satisfactory for the purposes of probability theory. But somehow in order to get this theorem, it seems to be what we need. With a larger choice of morphisms, this doesn't, I no longer know how to make this work. Alright, any questions so far?
Yes.
So I'll explain all of this, or maybe it's not a good. Yeah.
I just have some elementary questions about, like, what's fin unif?
Yeah, right. I'll explain that as well.
Okay.
So this is just some monodal category that turns out to be useful. I'll also explain the role that it plays.
The purpose of the talk is to explain this.
Yes, pretty much. Yeah. I just thought it would be nice to have everything kind of written down. And then to refer back to it and to see why I'm explaining, or why I'm introducing all this stuff. Alright, so let me now say what graded monads are.
So Tobias, that board will be blocked from now on.
Yeah. So very bad.
That backboard,
It doesn't
every
work.
other move of the boards will block it.
Yeah.
Oh,
So
right.
why don't you pull one of the other
yeah,
ones?
Yeah.
I mean,
Oh, there's one more. So there seems to be surprisingly little literature on graded monads, although so most recently they seem to have some computer scientists seem to be studying these a little bit more explicitly. But I feel like they come up in a lot of places, that many monads are secretly graded monads and are constructed out of as sort of by forgetting the grading. So let me recall, I'm kind of assuming that everyone knows what a monad is. So let me just recall that a monad on a category C can be equivalently seen as the lax monodal functor. So from the terminal category with rather trivial monodal structure into a category of endofunctors of C. Because on a single object here, we got an object in here, so an endofunctor of C. And for the lax monodal structure, we get, well, how do I, so the lax monodal structure is just, so let me call this F. The lax monodal structure is a morphism, in this case just a single morphism, pretty much, of F of 1 tensor F of 1 to F of 1, tensor 1. Right, so this would be the multiplication of the lax monodal structure. But because this is just functor composition, yeah.
Oh, sorry, no,
Oh.
you should finish your
So
sentence.
this is just functor composition, so in the end I got a the natural transformation from f of 1, composed f of 1 to f of 1. If you just write down all the usual, the conditions for this lax monodal structure, you get the associativity of the monad and so on. So this is the underlying functor of the monad, and this is the multiplication. So this is a kind of useful perspective for my purposes of what a monad is. And because now we can easily generalize this, because, well, now this looks kind of arbitrary, why do we put the monodal, why do we put the terminal category here? And so correspondingly a graded monad graded by another monodal category, G, is a lax monodal functor. Now I'm sure that you've guessed what it is. From G into n of functor 16. And yeah, there's also a more sort of highbrow definition of what a graded monad is in two categorical terms. Let me just write this down, and then if you may like it or not. So equivalently, a graded monad is what's called a lax algebra. Of the two monad given by G times on the two category of categories. So maybe you know that, I'm sure that all of you know that when you have a group, and then you can consider actions of the group on sets or in spaces. Those are the same as algebras of the monad G times. So G times, taking G times is an endofunctor of set or of spaces. And the multiplication of G makes it into a monad. And then the G spaces or G sets are precisely the algebras, and this is sort of now a two-categorical version of that. Alright, so just to illustrate, this is now just empty formalism. Let me give an example that is actually going to be very closely related to the probability, the categorical probability application. So let me take for the monodal category G that determines the grading, let me just take the natural numbers together with multiplication as a monoid. So the morphisms are trivial, are only identities, with only identity morphisms. So this is a monodal category. If you like equivalently, you can take finite sets with Cartesian product or categorical product, and then just take the skeleton, restrict to isomorphisms. No, sorry, I'm not sure. No, sorry, that's not equivalent. Yeah, right. Scratch that. So with only identity morphisms, let's take our target category C to just be the category of sets. Then I claim that the list monad is secretly a graded monad, graded by this category. So I guess has everyone seen the list monad? Or so the monad of the free monoid monad? Yeah. So this takes to every set X, assigns the set of words with the alphabet X, where X being star, whatever you want to call it. And this is clearly graded by length of the words, right? So it's disjoint union of the words of different length. I claim that if we start with a natural number n and assign to it the endo functor that takes the set x and maps it to the nth power. Well, so this is a functor from G into the category of endo functors. So taking the power as an endo functor. And that this defines a graded monad if I equip it with the multiplication. So for the multiplication, I need to take x to the n and now to the m. So this is the composite of, if I call this Lax-monadal functor f, then what I have here is sort of f of n, composed f of m applied to x. Right? Because just f of n of x, I've defined it to be this power. And the monadal structure on the codomain is functor composition. So this means I first take the nth power and then the nth power. And the multiplication now should take this to f of n times n, or n times n, applied to x, which means simply take x to the nth power. And so I need to say what this multiplication is supposed to be. And well, there's an obvious candidate. Suppose you can, basically by occurring, these are already isomorphic. A list, if you have a list of length m, whose elements are lists of length n, then you just concatenate them and get a list, these sub-lists, and you get a list of length n times n. So x11 to x1 m to xn1 to xnm simply maps to the list given by removing the brackets. Okay, I'm not gonna write down what the unit of the Lax-monadal functor is, so you'll just have to believe me that this becomes in the obvious way. So the graded list monad. So it's somehow an intriguing observation that this multiplication here actually has become an isomorphism. Yeah?
How do you forget the graded structure?
Yes, right, yeah, I'll get to that.
Okay.
Yeah. That's what this kind extension is about. Essentially by kind extension to the terminal monadal category. So the statement is that somehow I think many monads in nature are secretly graded.
Can you briefly name other examples? Like, I guess you're saying probably monads are also secretly graded. What about like the maybe monad or something? Is that too simple to me?
Right. I haven't thought, to be honest, right now I don't have any.
Okay, what about, okay.
Okay. But the maybe monad, I suppose, yeah, probably also graded by, if you just, so this is a guess at the moment, if you instead of the natural numbers, you take the monoid, two elements, right, that are, let's call them 0 and 1, such that 1 times 1 is, or 1 plus 1 is 1, and 0 is the unit.
And when you say secretly graded, do you mean secretly graded in a unique way, or do you mean that there could be more than, there could be many interesting
no, yeah, there could be potentially many interesting gradings, but I think I mean something more intuitive and vague that are somehow have a natural grading become equipped with, or can be constructed as can extensions in that sense of naturally graded monads.
Okay.
Graded monads that are somehow naturally graded.
Hmm.
It's not really any sort of intended to be very precise.
That makes sense to have some sort of universal property.
Yeah.
Yeah.
Yeah, and so, right, so now how do we make them ungraded? And this is actually very analogous to how you take a graded vector space or a graded algebra and make it ungraded. That turns out to be given by a kind extension. And likewise for the monads, we make them ungraded by sort of change of grading via kind extension. So this does not apply to all graded monads though, so we have some technical assumptions that now I don't want to get into under which this works. By change of grading. Through left hand extension.
The thing you're not wanting to explain is the technical assumptions under which this kind of extension exists.
Well, I don't want to. Well, I think in cat it will always exist, right? But under which conditions there is a unique monoidal, a unique lax monoidal structure on the can extension here. Well, okay, and I'm also for the existence in cat, I guess I'm also making certain assumptions about C. Yeah. But mainly the question is under which conditions this can extension can be equipped with a unique lax monoidal structure that makes this also the diagram also into kind extension in monoidal categories. So in the two category of monoidal categories with lax monoidal functors. So yeah, we have some. Well, really, there are in the literature some results along these lines called also kind extensions of this type are called algebraic, and there's results about when kind extensions are algebraic and that kind of thing. So that's what we use here. Okay, so to continue the example of the graded list monad, so this turns out to, this works. So the kind extension exists and is algebraic, so there's an reduced lax monoidal structure here. And so here, this, oh, I forgot, this was supposed to be denoted by L. L of, well, okay, I mean this is the terminal category, so let me also write L for the resulting endofunctor of C. And then this is just the list, the normal list monad, where we have the co-product of all these powers. So, Euclidean star. With its usual multiplication, given by, again, sort of removing the brackets. When you have a list of lists, you get a single list just by removing the brackets. But unlike in the graded picture, multiplication is an isomorphism. Here it's no longer an isomorphism. And this also happens, and it seems to happen in many cases. Also in our case, and that actually simplifies the technicalities that come up significantly with the combinatorics. This is how we get access to also higher spaces of probability measures like ppx, pppx, and so on. Okay, so this is just sort of heuristic observation. The multiplication of a graded monad is often invertible. Even if the one with the associated monad is not. Of the induced monad is not. Alright, so now we had, in the case of the list monad, we had taken these natural numbers here, right? And this is how we got this coproduct as the Kahn extension. Okay, so the Kahn extension sort of is pointwise, so it basically just takes the co-limit over the entire grading. And if we now talk about spaces of probability measures, then, as I was saying, we want to make precise the intuition that a probability measure is an idealized version of a finite sample. A finite sample is again kind of a list, right? But we don't care about the order of the elements. And another thing that we don't care about is whether we have a sample consisting of throwing a die 2 times, and we got a 1 and a 4. That is somehow the same sample as if we had thrown it 4 times and gotten 2 1s and 2 4s. So, in a sense, in order now, what I'm going to do is to take the graded list monad, or sort of something very similar to the graded list monad, by replacing the grading n by a differing category. Oh, and also want to replace sets, the category of sets on which the graded monad lives by complete metric spaces. So I want to change the category in such a way that 2 identifications of finite samples that I've just mentioned become implemented in taking the Kahn extension or this co-limit over there. And the grading that we need for that purpose is this category fin unit. Or actually, fin's going to be fin unit. Sorry, I think I had a typo there. Should be fin unit op. So objects are, well, again, we're going to deal with sort of the index. What indexes, the functors are again going to be, well, finite sample. The finite sample is indexed by its length. So we'll take the objects, we could take them to be natural numbers, but from a category theorist perspective, it's more convenient to work with finite sets instead. So let's take the objects to be non-empty. That is a bit of a delicate technical point. Finite sets. S. And morphisms are maps F from S to T with uniform fibers. What I mean by this is that if you look at the cardinality of a fiber of F, well, all these cardinalities should be the same. So in other words, they must be given by the cardinality of S divided by the cardinality of T. So for all elements little t. So in particular, we have that the Hom set from S to T is empty unless the cardinalities match up in the sense that the cardinality of T divides the cardinality of S. Okay, now I suppose everyone remembers the list monad as the graded monad. Because now I want to essentially write down the list monad again, but maybe, well, but with changing with a different version of the grading, namely that one. I mean, okay, I shouldn't be calling it list monad anymore, but it's very similar. So it's going to be fin unit A. So this is going to be the P star that I've mentioned over there.
Fin unit part is with times as the middle product.
Right. Yeah. Thanks. I forgot to say that. Yeah. So the Cartesian product of sets defines the monodal structure on that category. So this goes to again for wait, sorry, no, I'm reading the wrong line. So I want to define a functor like this. So it's going to take a finite set S.
You want to see that? Sorry.
Oh, yes. No, not yet. I mean, we can do this in two versions. Let me do it for set first, just to keep things simple. And then I'll extend it to CMet. So on set, this will take a set X. And well, previously we were taking the nth power. And well, we're still going to do the same. Now we're going to take the S power. So, which means the set of functions from S to X. Or think of it as families of elements in X indexed by the set S. Right, a function is a family of elements in X indexed by the domain of the function. Alright, and so concerning the functionality, now I really have to say what this is. Oh, and yeah, so these elements now are supposed to be the finite samples. Right, if you do a sequence of experiments indexed by X, then an X is your space of outcomes for a single trial, then this is going to be the space of samples for your overall experiment. And as far as probability is concerned, or relative frequencies are concerned, this has some invariance properties, and this is now related to the functoriality here that I'm about to define. If we have a morphism from S to T in fin unit, so without A, so this is just a function between sets having uniform fibers, then this becomes the natural transformation, and now this may be sort of looks a little large as in kind of lambda calculus-like stuff. So now I have to say what the resulting component at every set x is, and it should be a function that takes a sample, a finite sample indexed by t, to a finite sample indexed by s. And well, what it does is that it just takes the sample indexed by t, and I get a new sample indexed by s, and at s, it'll just be x f of s.
Is there something about the uniform fibers that's important in this, that allows this construction?
Not yet, no.
This can be made
No,
up.
you could do this just
set.
with fins. You could use fin set there. Yeah. You would just get a different ungraded. When you squash it down to an ungraded monad, then it would be a different one. At the moment, I don't actually know which one.
The point is you're copying your sample t over s times.
Pretty much, yeah. So this is exactly, yeah. In terms of, if you think of a sample as now representing a probability distribution, a finitely supported and uniform over these individual outcomes, then this, because f has uniform fibers, what this does is just to multiply each one by the corresponding multiplicity concerning the relative frequencies. The relative frequencies of the individual outcomes are the same. And in particular, if we just do a permutation, an isomorphism in the category, then it's just a permutation of the outcomes, yeah?
Is it equivalent, so without the relative frequency idea, this seems to capture the same data as just like a finite support function from x to n or something?
Yes, right.
Which counts just the multiplicity, but
Yeah.
so is the relative frequency idea equivalent to just like modding out by scaling, sort of like in projective space or something? You see what I'm saying?
Yes, and I think so. And this was in some sense originally where we came from, and we had been working with unnormalized, so just finite samples themselves and not introducing any sort of normalization thing, and seeing how those transport around between different spaces using coordinate vibrations and odd vibrations. But from the probability perspective, that didn't really seem to go anywhere. We're not sure what to do with that in the end. But yeah, I mean, I'm still hoping that maybe eventually something like that can be done.
We're about 10 minutes.
Okay, yeah. So now I can try to sketch why, if we take this can extension.
15 minutes. We started 5 hours.
Oh, right, yeah. Okay. If we take this can extension, so in this applies in this situation, and we do get an ungraded monad, or just an ordinary monad set. And this gives, turns out to be the rational convex combinations monad. Oh, I forgot to say what the multiplication is, right? But it's the same as before for the list monad. I mean, for that I haven't. Pretty much the same. So the rational convex combinations monad. And so meaning that it takes a set X and maps it to just the underlying functor on objects, maps it to the set of finitely supported probability distributions with rational weights. So just instead, it's not too interesting, but we already got something that goes in the direction of probability. So these are finitely supported functions. Summing to 1. Right. Is it kind of intuitive why we got this? So what we have to do is to take, for a given x, take the colimit over s in fin unif up of x to the s. And so then what we have in here are these finite samples, and each finite sample represents this uniform distribution over these outcomes, over its components. And we sort of identify 2 of them as soon as they have the same relative frequency, so that's guaranteed by our choice of morphisms in fin unif.
Why is this not over the integers rather, or the natural numbers rather than q greater than 0? Is because it has something to do with your uniform fibers?
Because these now represent, well, I suppose we could also, I could rewrite this by saying that now they take values in integers, modulo a bunch of identifications. But yeah, it has to do with that, in the sense that if you take, I mean, a priori, a finite sample is sort of a multi-set in X, and these identifications with uniform fibers, for example, lead to identifying the multi-set with X repeated with the multi-set just consisting of X, the singleton X. So hence it's useful to think of this one, each one of these is sort of having a weight of 1/2. And then this is weight of 1/2, weight of 1/2 is just the weight of 1 on X. So roughly speaking, this is how the rationals come in. So yeah, we think of this in a finite sample as corresponding uniform distribution, meaning 1 over cardinality of S weights. Yeah.
That's a right Khan extension, right?
No, this is should be left kind of extension.
Is the way you drew? Maybe I'm really confused. Okay, I'll just.
Oh, did I draw it the wrong way?
Well, your arrow goes up, but you might use the arrow going down.
But the natural transformation goes to p star, right? In the left Khan extension.
P is the Khan extension.
Oh, p is. Oh,
Yeah,
right,
yeah.
right. Sorry, I'm
P
so
of P
silly.
star along this thing, right? We start with the graded monad
I see.
and we squash it down to an ungraded one.
Oh, okay. Yeah, that makes sense. Sorry, I was just.
Yeah, no worries.
Yeah.
Okay, so the idea of the proof, I mean, I haven't really explained anything like a proof, only a sort of intuitive sketch. Morphisms in fin unif. Identify lists of the same relative frequencies. Or lead to an identification of lists with the same. Alright, but we had really wanted to get probability measures. So what do we do about that? I mean, these are kind of not really interesting as measures if they're finitely supported. And going to measures. Getting to measures is achieved by replacing the category of sets now by CMet. And using complete metric spaces is really what it's all about. So with just metric spaces, this would not work. Okay, so first of all, to define the graded monad, I need to say, well, I need to, for every S, I need to say what the corresponding endo functor should be. So that means I start with a complete metric space and I need to turn it into another complete metric space. I already know what I want it to be as a set, but I need to say what a metric monad should be. And, well, for a probability, seems natural to use the average distance. And that's exactly what turns out to work. Meaning that if we have one such finite sample and another one, then we simply define their distance as the average distance of these individual elements or outcomes. Yeah, then this is sort of almost like the usual monodal structure considered in the category of complete metric spaces. Or if you like Liouville metric spaces, it would be the usual. Yeah, but we need to rescale it by this factor. Okay, so then we get a finite op graded monad. On cement, yeah, this is the P star in the theorem. So now taking this CAN extension, changing the grading, to the trivial grading. Gives what we've called the Kantorovich monad, and that's because so we've called it the Kantorovich monad because the metric that we get on Px for a complete metric space X is this Wasserstein distance, which comes from Kantorovich's theory of optimal transportation, and Kantorovich duality, all that stuff. So maybe here you can see that for those of you who know a little bit of this theory, if you have two finite and uniform distributions and look at the Wasserstein distance, it's going to look exactly like this, but when you minimize over the possible permutations, so you're allowed to insert a permutation here. So then it would be sort of min sigma permutation sigma, and then you put your sigma of S, sort of optimally matching up the elements of the first family with the elements of the second family. And this matching up is also achieved by taking our colimit over fin unit because the permutations are in there. So this is roughly speaking, or indication of how this comes about, that we get this L1 Wasserstein distance on Px. All right. Yeah, I think that's pretty much what the material that I had. Yeah, the equivalence of the P algebras and the P star algebras for us do not to be still some additional work. But I feel like it's probably an instance of a general fact about two monads and two categories, that under suitable assumptions you get, if you do this kind of kind extension thing, you also get an equivalence of categories of algebras, but we haven't worked out the general two categorical details of this. Yeah, but I feel like it's an interesting problem. Alright, yeah, as I said, and then this equivalence also gives us a combinatorial notion of integration. Yeah. Alright, that's what I have for today. Thanks.
At the perimeter, they do physics.
Right.
Can you give me the physical motivation of what you're doing?
I'm afraid for this stuff there I don't have any physical motivation. I happen
Like
to be
quantum probabilities or
right. No, I don't have anything to say about that.
okay.
Yeah, I happen to be there for other reasons because I've previously worked more in that direction, and they seem to have liked that stuff, and so now, yeah.
Nice place to park yourself for a while.
What would you get if you did include the empty set in fin? You would still get some graded monad, and you would still make this
right.
definition.
Yes, I think what happened then is that the resulting monad completely breaks down. So then the empty set would be initial and fin unif, right? So terminal fin unif off, meaning that the colimit completely collapses.
So you've said lots of monads are secretly graded monads. Can you replay some sort of same story just in set and think of a lot of monoids as secretly graded monoids?
Good question. I don't know. Yeah, I haven't thought about that. Right now I can't think of any interesting...
Could you construct Q or something if you...
Construct what?
Could you construct the rationals if you, I don't know, you had some maximum modal factor from fin unif to set? And you can't extend that along the map to the terminal category.
At the moment I don't see how, so yeah.
Okay. Yeah. Cool. Any other questions? Yeah, well, let's thank Tobias again.